alkynes. All right, alkynes are hydrocarbons with triple bonds, as you know. We have the infrared spectrum. You have this characteristic stretch at about 2200 wave numbers, and that's a C triple bond C stretch. This is a region where we see multiple bonds, right? C double bond C, like 1650. This guy's at 2200. If you have a terminal alkyne, right, with an H attached to that carbon, you see this pretty intense signal at about 3300. So they're pretty easy to see. All right, let's name alkynes. They have 2 degrees of unsaturation, as we said. They can be internal, like this guy, or terminal, where the triple bond's on the end. All right, to name them, you start with the alkane name, right, ethane, and you turn it into ethine. All right, this one gets a common name, acetylene. All right, you've probably heard that, oxyacetylene torches. All right, this one's going to be 1, 2, 3, 4 carbons. So we call that 1, or just, I suppose we say 1 butine. This one's got, let's see, numbering from this side, 1, 2, 3, 4, 5. So this will be 2 pentyne. You could call it pent-2-ine as well. Here we go. Let's see what our number from this side, 2, 3, 4. Now this one's mean because this ethyl goes up. So the longest continuous chain is a hexyne. So we need to say 4 methyl 2 hexyne. Here we have some enines, and they're named that in that order. So they both have equal priority. So you number from the side that appears first. 1, 2. This is kind of weird, but there's a carbon in there, right? This means this. All right, so an enine. So we have an ene at 5 and an ine at 1. And the total length is 7, so it's heptyne. So it's going to be 5 heptene, 1 ine. And is that E or Z? It's E, right. This one, because the alkene's closer to the end, we number it this way. 7. Again, 2 carbons here. So this is also a heptenine, and let's see, so we call this 1 heptene, 5 ine. Here we have a diine, a polyine. Number from this side, 1. Remember, those are carbons. 2, 3, 4, 5, 6, 7, 8. So it'll be 1, 3, octa, diine. Kind of weird, but there you have it. All right, what are we going to do with this guy? They're equally, it's an enine again, but the alkyne is on carbon 1, or the alkene is on carbon 1. It's a tie. So what do? They had to make up a rule, and I think they went alphabetically. Alkene beats alkyne. So we're going to number from this side, but we still name it an enine. So it's going to be 1 hex, 1, 2, 3, 4, 5, 6. Weird. 1 hexene, 1, 2, 3, 4, 5 ine. And finally, we got this one, longest continuous chain. In this case, we want to keep the alkene and alkyne on the main chain. So let's call it this 4, 5, 6, 7. 8, even though it would be 8 this way, it's harder to name this guy with the alkene in it. So let's name it this way, and we'll put a butyl on there. So it will be 4 butyl. Be an enine, 5 heptene, 1 ine. And we can say it is also E. All right, and that's naming alkynes, so be able to do those. Other functional groups, so priority goes in terms of oxidation. So the most oxidized functional groups have higher priority. alcohols, betamines, alkenes, alkynes are equal. And the double bond gets the number if it's tied with a triple bond. Okay, so this is an alcohol with an alkene, so it's going to be named as a propanol, but we would call it 2-propene, 1-ol. Same thing here, we have to number from this side because the alcohol gets priority, so it's going to be 4-pentine 2-ol. And we already saw this before, but by definition, the hydroxyl group in a cyclic alcohol is carbon 1. So it will be 3-cyclohexene-ol. Or we could say 1-ol if we wanted to, but it's understood that it's on carbon 1. All right, so physical properties, they're very similar to alkanes, alkenes, right? Alkynes are insoluble in water. They're nonpolar. They're soluble in nonpolar solvents. They have relatively low boiling points because even though they're slightly more polar than alkanes, they're still relatively nonpolar. Alkynes have slightly higher boiling points. I just said that, didn't I? All right. The structure. So let's just look at acetylene. All right, what's the hybridization on these carbons? It is sp hybridized. All right. So the bond angle here is going to be 180 degrees, as we know. And if we think about hybridization or how we would draw this thing, I draw my sp hybridized carbon, forming a sigma bond with my other sp hybridized carbon, sigma bonds to H, and then we need the pi bonds, right? So we need the p orbitals. So we'll have this p orbital, and we'll have this p orbital, and those overlap to give me the 2 pi bonds. So 3 sigma bonds and the 2 pi bonds. So we know this. Synthesis of alkynes, we're using dehydrohalogenation. So you can start with vicinal dihalides, right? We can make those starting from an alkene by halogenation, can't we? So we go through the bromonium ion, we get anti-addition, but we get vicinal dibromides. Remember that KOH with a halide, right, with a beta hydrogen adjacent, strong bases, take those protons, electrons fall down, it goes, and you form alkenes, right? Dehydrohalogenation. In this case, we have an H and a Br, and an H and a Br, so we do it twice, and what we get is the alkyne. Benzenes. So sort of 2 equivalents of dehydrohalogenation gives me the alkyne. This is a similar deal. This guy, we're going to use him later on too. So this is called amide. So NH2 minus is a very strong base, right? His conjugate acid is ammonia, and the pKa of ammonia to lose a proton is about 35. So it's not very acidic at all, which makes amide a very strong base. We have 2 equivalents, and right, you pair it with sodium. Sodium's just going to be a counterion. If it dissolves in it, we just ignore it. So here, when this first sees a strong base, what are we going to do? Right, we have a hydrogen here, so we can do dehydrohalogenation, but the pKa of alcohols is about 16, which means it's relatively acidic. So what happens with the first equivalent is it's just an acid-base reaction, where we take away that proton plus ammonia. All right, then if we do it again, now we're going to do our elimination reaction. Right, and so we'll get the product that we were looking for. Oh, this guy, oh, bad work. And then second step, right, this is called acid workup. So I'm treating with HCO plus, and we'll end up with the protonated alcohol. All right, so this is super important, right? Dehydrohalogenation is really important to recognize. This thing is just sort of an interesting case where now if we think about it, if you have an acidic proton like an alcohol or a carboxylic acid, if you treat that with a base, right, I want it to react with this hydrogen, but it's going to do its acid base first. So just kind of thinking about acid-base reactions as we're thinking about organic synthesis. We'll talk about reactants next.